talking about the typical embedded system. In my previous video, you must have seen an introduction to embedded systems where we talked about what an embedded system is, how they are classified, what purpose it is made up for, and a few examples related to that. In this video, we'll try and focus on what an embedded system is actually made up of. Like a typical embedded system, it consists of many components. 6 of them have been noted down here. They are core, memory, sensors and actuators, communication interface, embedded firmware, and other system components. To keep this video short, I will divide this section into 2 parts. In this video, I'll be talking about details about the core, memory, and about sensors and actuators. And in the next video, we'll go deeper into talking about communication interface, embedded firmware, and then talk about some other system components. Embedded systems are domain and application specific, and they are built around a central core. If you look at the core can further be divided into further classifications. Almost 80% of all embedded systems are made from general purpose and domain specific processors. The rest are made from application specific integrated circuits, ASICs, or programmable logic devices, or commercial off-the-shelf components. Let's dive deeper and see what general purpose and domain specific processors are made up of. General purpose and domain specific processors can be further divided or classified into microprocessors, microcontrollers, and digital signal processors. If we focus our attention onto microprocessors, we find out that microprocessors are made up of arithmetic logic units, a set of special or general register arrays, a control unit, and a specific instruction set. The companies that deal or who are big players in microprocessors are Intel, AMD, Freescale, and IBM. Microcontrollers, on the other hand, are highly integrated chips that contain a CPU. Now, apart from the CPU, they have a scratchpad RAM. They've got further register arrays. They've got on-chip ROM flash for storing programs. They've got timers and GPIO, which is general purpose input-output devices, and interrupt controllers, and many more things. So all of these components, they come together and they are put onto one IC, and that is what a microcontroller is. One of the questions that you may have, or someone else may pose you now, would be, what is the difference between a microprocessor and microcontroller? So let me list them out for you. A microprocessor is a CPU which can do math and logic and has instruction sets, whereas now a microcontroller can be made up of a CPU plus RAM and ROM and different peripherals. The microprocessor is a dependent unit. Like, to build an embedded system around it, you will need so many other things, and you will have to put things together on a PCB and interface them. So it depends on so many other things. Whereas a microcontroller, for the most part, is self-contained. Many of the things that you require for an embedded system is already put that on that IC. A microprocessor is general purpose, so it can be used for a variety of different applications. Whereas if you see a microcontroller, it is generally application oriented, so designed for a specific application. Because of that, they have peripherals that are again optimized for that particular application or domain specific. The microprocessor will not have any IO ports, and to deal with any input and output devices, you will need different interfacing logics to put them together. Whereas a microcontroller, it is rare to see that a microcontroller has no IO ports, or rather, you will always find that a microcontroller has multiple IO ports. In a microprocessor, you've got limited power saving options. Whereas on a microcontroller, there are lots of power saving features. Digital signal processors are specifically designed to meet the embedded audio, video, and communication applications demand. They are up to 2 to 3 times faster than general purpose microprocessors for signal processing applications. Now, they are able to do that because they implement most of the computational logic in hardware. Computational logic like addition, subtraction, multiplication, division is programmed into the hardware, and hence it makes them very fast. After having covered the big option that is there for core, let us dive deeper and see What are the other options available? One option that we have is application specific integrated circuits, or as they're called ASICs. Now, they are designed to perform a specific or unique application. They stand as a replacement to conventional general purpose logic units. It integrates several functions into a single chip and thereby reduces the system development cost. Now, most ASICs are proprietary products. Since they consume a very small area, it helps to design a smaller system with higher capabilities and functionalities. Now, they are made using reusable building blocks. They are only profitable if they are made in large volumes for commercial productions. Now, fabrication of an ASIC requires a non-refundable initial investment for the process technology and configuration expenses. Now, this investment is known as non-recurring engineering charge, NRE, and it is a one-time investment. Logic devices provide specific functions, including device-to-device interfacing, data communication, signal processing, data display, timing and control operations, and almost all other functions a system must perform. All of this is packed into one device. Programmable logic devices are also called PLDs. With PLDs, designers use inexpensive software tools to quickly develop and simulate and test their designs. Then a design can be quickly programmed into a device and immediately tested in a live circuit. The PLD that is used for this prototyping is the exact same PLD that will be used in the final production of a piece of an equipment. Now, because of this, there are no NRE costs involved, and the final design is complete much faster than that of a custom fixed logic device. PLDs can be further classified into CPLDs, that is complex programmable logic devices, and FPGAs, that is field programmable gate arrays. Now, CPLDs, they have less number of logic devices, about 10,000 gates. They are very predictable in timing, and hence they can be used for critical applications. They have low power consumption and cost very cheap. On the other hand, FPGAs, they come up with a huge amount of logic density, about millions of gates packed in together. That is why they provide lots of features and they've got faster performance. FPGAs are also used with ASIC designs. ASIC designs are tested on an FPGA by a designer. They program it and they test it quickly. Once that is finalized, FPGAs can be converted into ASICs. Finally, we come to our last classification, commercial off-the-shelf components. Now, they are used as is. That is, COTS products are designed in such a way to provide an easy integration and interoperability with existing system components. Now, the COTS themselves may be built around a general purpose or domain-specific, processor, but they're used in collaboration with other embedded systems as a peripheral. Now, the major advantage of using COTS is that they are readily available in the market. They are cheap and a developer can cut down the development time to a great extent. This in turn reduces the time to market your embedded systems. Here I've shown two very interesting products. On the left hand side, we've got an ESP device. ESP device is a small embedded system that can connect to existing Wi-Fi networks, or it can create a Wi-Fi network of its own. So it supports IoT. If we can fix it with any existing embedded system, we can give it IoT kind of features by adding this COTS product. On the right hand side, we've got STM32F4 discovery board. One can build an embedded system around it, or it can also be used with an existing larger embedded system. So maybe if you want to just add UI features, you can connect this device with an LCD screen and interconnect it with your existing embedded system. So in this way, COTS products, they help to expand your embedded system with further options and features, or you can actually go around and build your embedded system based on these products. Rather than buying a microcontroller and programming it, you can buy the products and build an embedded system around it. After having talked about the core, let us move on to the next topic, memory. Memory can be further classified into two parts, program storage memory, also called as ROM, and random access memory, called RAM. If we look into the program storage memory, there is also the code memory. We can further say that the code memory can be stored into several different places. One option we have is the masked ROM. The masked ROM is hardwired technology for storing data. So it is factory programmed, and because of that, it has low cost and high volume production. The second option that we have is programmable read-only memory. Programmable read-only memory is not pre-programmed by the manufacturer. and one can actually program it. Once you buy it from the market, it is blank. You can program it with your code. But once it is programmed, it cannot be reprogrammed again. The next type of memory that we have is an EEPROM, also called as erasable programmable read-only memory. Now, the PROM that we had seen earlier, they are not useful for development purpose, because when you're developing, you would want to write code, erase it, write code, erase it, and check things out. EEPROM gives us the flexibility to reprogram. But to reprogram it, you have to pass the chip through an UV eraser device. So it's an ultraviolet eraser device, and it takes up to 20 to 30 minutes. So it is tedious and time consuming. The other option that we have further is electrically erasable programmable read-only memory, or EEPROM. As the name suggests, EEPROM is electrically erasable. That is, you can erase the device using some electrical signals, and it takes only a few milliseconds. The only limitation is that the capacity is limited when compared to a standard ROM. Flash is the latest ROM technology that we have. It is actually a variation of the EEPROM technology. Here, the flash memory is organized as sectors or blocks or pages, and the flash memory stores information in an array of floating gate MOSFET transistors. The erasing of memory can be done at sector level or page level without affecting the other sectors or pages. Each sector or page should be erased before reprogramming. The typical erasable capacity of flash is about 1000 cycles. Next we have NVRAM, which stands for non-volatile RAM. It is a random access memory with battery backup. It contains a minute battery for providing supply to the memory in the absence of an external power supply. So even though it's a RAM, the memory is not volatile because the battery holds the charge there. Now that we have discussed about ROM, which is the program storage memory, which needs to be stored even when the power is not there, let's talk about the next kind of memory, which is random access memory. Now this is the data memory or the working memory of the controller. The controller can read from it and write to it. The RAM is volatile, meaning when the power is turned off, all the content is destroyed. RAM is direct access memory, meaning we can access the desired memory location directly without the need for traversing through the entire memory location to reach the desired memory position. Okay. So RAM is further classified as static RAM, dynamic RAM, and non-volatile RAM. Static RAM stores the data in the form of voltage. So they're made up of flip-flops, and they are the fastest form of RAM that is available. Whereas dynamic RAM stores the data in the form of charge. They're made up of MOS transistor gates. The advantages of DRAM is that it's high density and low cost compared to SRAM. And the disadvantage would be, since it is stored in the form of charge, the charge gets leaked off with time, and hence they need to be refreshed periodically. Because of that, we've got DROM controllers that are used to refresh it periodically in milliseconds of intervals. Non-volatile RAM, as discussed earlier, is non-volatile random access memory with battery backup. Any embedded system is in constant interaction with the real world, and the controlling and monitoring functions executed by the embedded system is achieved in accordance to what happens in the real world. Just like our eyes and ears are inputs from the external world to our brains, and what we perceive through them, we end up in reacting with our hands. Similarly, for an embedded system, sensors act as input from the external world to the embedded system, whereas actuators help to take actions based on those inputs. A sensor, by definition, then, is a transducer device that converts energy from one form to another for any measurement or control purpose. And an actuator is a form of transducer device, mechanical or electrical, which converts signals to corresponding physical actions, that is generally motion. An actuator acts as an output device. At a later stage, we'll discuss in detail about different kinds of sensors and actuators. But just in brief, we'll see a few of them here. Common actuators and sensors used in embedded systems are LEDs, 7-segment displays, optocouplers, stepper motors, different kinds of relays, piezoelectric buzzers, 8255 peripheral interface ICs, push buttons, and hex pads or keyboards. With this, we come to an end or part 1 of this section, typical embedded systems. what we have discussed in this video are the different types of core options that we have, the different type of memory options that we have, and different types of sensors and actuators. In the next video, we'll talk a bit more about communication interfaces, embedded firmware, and other system components. Thank you for watching this video. If you liked the video, give it a thumbs up. With this, I sign off. Your friend, Elijah. Thank you for watching once again.